Hi everyone, today we're going to talk about periodic trends. So there's four you'll need to know: atomic radius, ionization energy, electronegativity, and electron affinity. So we'll talk about what they all mean and how to recognize and understand the trend from the table. So the first one you'll need to know, and the most important one, because if you understand this one really well, you could get all four. The first one is atomic radius. So of course the radius of a circle is just the center to any outer point. So atomic radius is just the way that scientists measure the size of an atom. If something has a greater atomic radius, it's bigger. So let's talk about atomic radius. Let's say this one. Let's say we start off at 1 and it looks like this. We're going to use the Bohr model for all these trends to help us understand. Even though it's not the best representation of a molecule, it's the most helpful one to understand the periodic trends. So this inner circle is the nucleus, and then these are outer shells of electrons. So let's say we start off here. As you go down the periods, you're adding electron shells. So if I were to go down by 1, I'm adding a new shell. So it's going to be like this. I'm going to add a shell to have 3 shells. So notice how very clearly this is going to have a radius this big, and then that corresponds to this here, and then we added a whole new shell. So that's going to make it bigger. So as you go down the periodic table, you're adding more electron shells and you're getting bigger. Now let's consider left and right. When you go left and right, you're not adding or subtracting any electron shells. You're in the same electron shell. Instead, what's happening when you go left to right is, let's say I go 1 to the right. All what's happening is I'm adding 1 electron and I'm adding 1 proton. So when I add 1 electron, 1 proton, what happens? Let's consider a molecule that looks like this. Let's say there's like 1 positive here, and then like that. Let's say these have a bunch of electrons, whatever, and then there's 2 out here. Now I'm going to go 1 to the right. When I go 1 to the right, there's going to be 1 more proton, so there's going to be 2 pluses, and then of course these are staying the same. And then what happens to my valence electrons is I'm going to add 1 more electron. So this has 2, and now we're going to add 1 more to be 3. So what's going to happen is we know positives and negatives attract. So in this one, there's 2 positives. So these 2 positives are going to attract all of the electrons inward with a stronger attraction than this one, because this one only has 1 proton. So this one will still attract it, but it's not going to be as strong as this. So why does this matter? Because this one has stronger attraction, everything's going to be pushed inward because there's stronger attraction, and it's going to be smaller. So as you go to the right, you're adding more protons, and because of that, there's stronger attraction, and because of that, everything's attracted more inward and it gets smaller. So it's more helpful to remember this trend of getting smaller. So if you go up the trend, you get smaller because you have less shells, and if you go to the right, you get smaller because you have more attraction and everything becomes smaller because of the stronger attraction. One important thing I should add is, okay, let's compare like Si to Se. Which one's bigger? So Se has a whole new shell. So okay, Se should be bigger, but Se also has 2 protons. So how do I know which effect is bigger? The rule of thumb is generally that 2 to the right, 2 or more of course, to the right is going to have a bigger effect than 1 down. So that's like a general rule. So here I'm going 2 to the right and 1 down. So 2 to the right is going to have a bigger effect. So Se is smaller even though it's down. So let's compare maybe now Al to like Br. Br again is 1 down, but it's all the way to the right. So that effect from going right is going to be more prominent than the effect of going down 1. So Br is going to be smaller. You will pretty much never be asked to compare something like Si and As because that's usually a toss-up. But the general rule is if it's 2 to the right, usually that effect will be bigger. So Se will be smaller. So this is the most important trend to understand. Now let's move on from here. Let's do ionization energy. Ionization energy is how much energy is needed to take an electron off. So if my molecule looks something like this, how much, I'm going to ignore the inner shells, how much energy is needed to take one of these outer electrons off. That's what ionization energy is. So again, let's do the same thing and consider this. We could reason through atomic radius. So let's imagine something is here. And we said when you go to the right, you're smaller. So let's have this be molecule A, and something like here be molecule B. So we can agree that A is smaller than B, okay? Because A is to the right. Now, because A is smaller than B, and it's literally smaller like this, compared to B, which could be bigger, like maybe like that, it's going to be much easier to take an electron off here. And that's because these are physically farther from the nucleus. So this positive and negative attraction is much weaker here because they're farther. So because the attraction is weaker, it's going to be easier to take this off. Now imagine, look at here with molecule A, which is smaller. This electron is so close to this positive. The attraction there is super strong. It's going to take so much energy to take it off. So what you got to know for ionization energy is anything that is smaller has higher ionization energy. So that means if smaller is up and to the right, that means ionization energy gets larger as you go up and to the right. Because smaller things have higher ionization energy. It's harder to take an electron off something that's small and everything's inwardly attracted. Now let's talk about electronegativity. So what electronegativity is, let's imagine we have a covalent bond between F and Br. A covalent bond is electrons being shared. Now what electronegativity says is that most of the time these electrons are not shared, not most of the time, but sometimes electrons can be shared not equally. So even though they are shared, they're not shared exactly the same. So what electronegativity says is the element with higher electronegativity, so F is more electronegative, that means the electrons are going to be technically closer to the F. And I'll show you why. How does this trend work? So let's, again, imagine our F and Br. We know F is smaller than Br because Br is lower, so it's got more shells. So let's draw F like this, and then let's draw Br like much bigger, like that. What is this? So what's going to happen is these electrons are being shared. But what's really happening is this nucleus with positive charge, sure, it's pulling the electrons a little bit here, but look how much closer this positive charge is to the shared electrons. This positive charge is right next to the shared electrons. So this positive charge is going to attract the shared electrons very strongly. So what that means is because F is smaller, its protons are closer to the shared electrons. The shared electrons are right there, and F's protons are right next to it. That means F is going to pull the shared electrons more to its side, and that's exactly what electronegativity is. So even though this is a covalent bond of shared electrons, they are shared, they are much closer to F because F is attracting them more. So the trend is, as something gets smaller, as we saw with F, it's got higher electronegativity. So smaller is going up, that means higher electronegativity, call it En, is up. And then electronegativity, same thing here. So something smaller has higher electronegativity. Last thing we'll talk about is electron affinity. Electron affinity just says we got a molecule here, and then how much energy is released when we add an electron. That's the exact definition. So to understand it more frankly is, this is how I like to remember the trend. It's like, let's say I have a small get together with my friends. It's just 5 people. So it's a very small outing. And then one more person that's kind of unwanted wants to join. So here's our small group of friends. We're small. And then this one unwanted electron wants to join. We're going to release a lot of energy. We're going to be like kind of upset. It's going to be very noticeable that the group is disrupted because we only got 5 friends and then this one new person's coming in. Now let's say it's a massive party with everyone down the street and everyone you've ever seen's in this party, people you know, you don't know, and it's a much, much bigger outing. And then one person that you don't know shows up. You're probably not even going to notice. And that's exactly what electron affinity is. How much energy is being released when you add an electron. So something that's bigger is going to release very little energy when electrons added, because this is barely going to release energy. The positive charge is so far, it doesn't even notice this electron being added. Whereas if you have something much smaller, this is going to release a lot of energy. I mean, the positive charge in the nucleus is right there. It's going to be like, I don't like this. I'm going to release a lot of energy. So that's what electron affinity is. So as you get smaller, you have higher electron affinity. You're releasing more energy when you add an electron. So if smaller is up, that means we're going to have higher electron affinity as you get smaller. So smaller is to the right. That means, let me erase this. As you go to the right and smaller, you're going to have higher electron affinity. So that's your periodic trends explained. One very common problem is they'll show you like a table and they'll say, this is how much energy is released or how much energy is required. I just spelled required wrong, I believe. How much energy is required to remove that electron? And they'll say first, second, third. And then the first could be like 500. And the second will be like 1,000. And then all of a sudden the third will be like 7,000. And you're like, hey, why this huge jump? And that's because this is representing a molecule somewhere here. Let's imagine like beryllium. Beryllium has 2 valence electrons. It's got one here and one here. It's 2. It's group 2. So if we draw beryllium, it's going to take a bit of energy to remove this. Okay. It's going to take a bit more energy to remove this. Fair. And then if you want to remove anything more, now we got to go to an inner shell. We're done with this shell. There's only 2 valence electrons. So that third ionization energy, that third amount of energy required to remove the third electron is going to be from an inner shell. So of course, inner shell that's much closer to the nucleus, that's going to be much harder to remove. So that's a common problem. They could be like, hey, what element is this representing? And then you'll say, okay, first requires a bit, second requires a bit, third requires tons. So that means it's got to be something with 2 valence electrons, because once you lose the 2 valence electrons and you try to get rid of the third valence electron, it needs tons of energy. So that's just a common problem. Thank you for watching, and I hope this video helped. There's probably be another video dropping soon about exceptions in periodic trends. It's more of an AP concept.